Okay, let's begin my today's session. But before I start, I must tell you that I hope you are all sitting with your calculator. That calculator may be a scientific calculator or the calculator inside your mobile phone. Because yesterday, when I had class with CSE section B, I asked them to do a sort of calculation because I didn't have any calculator at that time. My calculator was actually it's broken, and my mobile was getting charged. I couldn't get hold of the calculator. I was not able to solve the problem, to do the calculation. So I asked them. Only one student was doing the calculation, but later he told me that his calculation was actually wrong. So I need, in today's class, if I ask you to do calculation, at least one people must give me the reply, so that I can compare that everybody is in line, in correct direction. So please help me only with the calculation. I'm not asking you to give me the answer. I'm not asking you to solve the problem. I'm asking you to do the calculation. I can expect at least up to this, I think. So yesterday I was very much disheartened. I don't know. Yesterday you got your MS Team ID. Probably at the time when I was taking the examination, the class, I doubt they were doing some sort of activity with their MS Team ID. Nobody replied. So a strange thing happened yesterday with CSE section B. So I don't want that this should repeat in this particular class. Otherwise, I'll stop teaching you if you do not do the calculation at least. Anyways, my today's topic is hypothesis testing. And I was teaching hypothesis testing since I have been teaching this topic since for last 4 days. Today, I'm going to give you some different aspect of that. I'm going to deal with two types of error. One is called type 1 error, and another is called type 2 error. I'm going to explain what these errors are. Okay. Now, in hypothesis testing, what do we actually do? We actually set the null hypothesis H0 and we test it. That is the basic objective of the hypothesis testing. Now, two things may happen. One thing is that your null hypothesis that you have, the hypothesis that you have assumed about the population, this null hypothesis is indeed true, or your null hypothesis is false. These two cases may arise. Suppose I am declaring something about the population mean, or declaring something about the population standard deviation. Say, for example, I'm saying that now all over the world, the percentage of COVID affected people is less than 50%. Suppose I'm saying like this. So I'm actually saying that on an average, 50%, less than 50% people are COVID affected. So conclusion is that the COVID wave is gradually decreasing, be it first wave or be it second wave, whatever. And suppose we have collected the sample and we tested it somehow with some statistical tool. Then, according to the calculation, two things may happen. What are these two things? We may accept the null hypothesis that we have set up corresponding to the situation, or we may reject the null hypothesis. Okay, these two things may happen. And when I'm doing this on my part with respect to sample, on the basis of sampling, then suppose my declaration about the population or about the COVID affected people of globally is actually true. I have actually guessed it correctly, and I am accepting the null hypothesis. That means your assumption H0 is true, is correct, and with respect to the sample, the way you have chosen the sample, you're also going to accept the null hypothesis. then there is no problem. It will be, this will be super fine. Null hypothesis was indeed true, and we are accepting the null hypothesis. This is one case. Suppose my null hypothesis is false, that no, COVID is actually increasing globally. COVID affected people is not less than 50%. Okay, it is more than that. And suppose we have assumed that the COVID affected people is less than 50%, but we are rejecting the null hypothesis. Suppose the global scenario is actually the COVID is not decreasing. It is in dormant stage. And according to our sample, we have also come to the conclusion that the corresponding null hypothesis is not true, it is false. So when null hypothesis is false and we are rejecting null hypothesis, then it is all right, no problem with that. So we shall consider these two parts as no error part. Actually, we have not done any sort of error over here. You can very well understand this. But suppose our null hypothesis is true. Our null hypothesis is indeed true that suppose the COVID affected people, I'm writing this statement over here, average number of COVID affected people globally is less than or equal to 50%. Okay, suppose this is my null hypothesis, H0. Now, suppose this statement, this assumption which I have made about the population, it is actually correct. But I have a person has selected the data from March 21 till June 21 from India. India is the part of this whole world, and his whole sample is from India. Then definitely he is going to reject the null hypothesis, because of the situation we all know that happened in India and have been is happening right now till now. So he is going to his null hypothesis, he is going to reject his assumption about the global condition of the COVID-19 patients. But suppose the problem is only with India and not with other countries. Suppose this is the scenario. All over the world, it is actually reducing, but he is rejecting the null hypothesis on the basis of the sample drawn from India. So null hypothesis is true, but he is rejecting the null hypothesis. This is a kind of error. Such an error is called type 1 error. Such error is called type 1 error. And suppose the null hypothesis is false. Suppose the average number of COVID affected people is actually greater than 50%. So my H1 is this average number is greater than 50% globally. Okay. So, and we have selected this sample from a particular country, say, as for example, say New Guinea, and there, according to the World Health Organization's current data, in the New Guinea section, in this country, from March 21 to June 21, COVID affected people's percentage is low. I have collected the sample from there. Actually, I am the experimenter. I am not collecting the sample. I am letting my people to collect it. I'm getting the data from somewhere, from some source. And from this result of New Guinea, I am accepting my null hypothesis that, yeah, actually globally, the COVID-19 situation is actually, it is good. It is improving. But suppose it is not the case. It is only case with, it is the case with only New Guinea. It is not the global case. So I am going to accept my null hypothesis, whereas my global assumption is actually false. So this is a kind of error which is called type 2 error. So we have got two different kinds of error. One is called type 1 error, another is called type 2 error. So let me write the definition. So I have written the two definitions. One is type 1 error, rejecting the null hypothesis H naught when it is actually true is defined as a type 1 error. But here you carefully observe the word I have actually used. I'm writing failing to reject the null hypothesis. Failing to reject the null hypothesis means you can say that complementary to this particular word, I can use accepting the null hypothesis. Failing to reject and accepting, are they synonym? Are they opposite to one another? Failing to reject and accepting, probably you are thinking that um, these two words are opposite of one another. Okay, they are opposites. But actually in statistics, that statement failing to reject has carefully been introduced. Whenever a person writing that accept null hypothesis when it is false, that means he is saying that, okay, he is determined that he has done something wrong with his data. But whenever a person is writing like that, the failing to reject the null hypothesis, that means some sort of doubt is in mind. Probably he is also thinking that whether have I done correctly or in a wrong way, because everything depends upon the choice of the sample. Is my sample all right? How has it been collected? All the questions are coming to his mind. The actual scenario that he is seeing all around, probably it is not matching with what he has got. So he has some sort of doubt in his mind, and therefore he is not writing accepting the null hypothesis. He is writing that failing to reject the null hypothesis on the basis of my sample, when actually it is false. This is called the type 2 error. So right now, right at this moment, I'm actually going to talk about type 1 error first. Type 2 error will be discussed later on. Now, I'm coming to the most important part, that first of all, I'm going to write the definition on the board, and then I'm going to explain what sort of, what is it? Okay, I'm going to explain that definition using a particular problem. Okay, and you will understand, because this sort of problem has already been done in the class, but its meaning has not been discussed properly. Now I'm going to write the definition in the next page. Probably I hope that you have taken the screenshot of this page. You see, two definitions have been written over here. I'm actually defining a probability. Whenever I'm actually rejecting the null hypothesis or accepting the null hypothesis, I'm doing it with some sort of probability. That probability of rejecting the null hypothesis when it is true is being denoted by alpha, and probability of failing to reject the null hypothesis when null hypothesis is false is being denoted by beta. Now you will be glad to identify or glad to see that what I'm going to write, what I'm going to name for this kind of probability which we have denoted by alpha. Probably you do not know what alpha is, but you know its name, and we have already used its name in our problem. Such a probability, alpha, is called level of significance. In the problem, we have used the word level of significance several number of times. Level of significance is the probability of committing the type 1 error. Sometimes type 1 error is also called producer's risk. It is called producer's risk, and type 2 error is called consumer's risk. From management perspective, from business perspective, producer's risk is far more grave than the consumer's risk. So this issue is very grave issue. If you want to compare the two issues with which error is very dangerous, then always remember that this particular issue is very dangerous. Producer's risk or type 1 error is very dangerous. Okay? Remember this. I'm not going to explain it right now. Now, level of significance, we have used different sorts of level of significance, like type 1 error, like 5% level of significance or 1% level of significance. We have used different sorts of level of significance, you know. Now, according to the scenario that I have explained over here, if I draw a normal curve, and if I take a normal population like this, okay, and if I denote this point like 1.96 and this point as minus 1.96, if you calculate, and suppose capital Z equal to 0, and this you calculate the probability of this region, okay, then you will come to know that this probability gives you 0.95. This is easily calculated with the help of normal table. If this is 0.95, then this part will be this part and this part together will give you how much? 0.05. If this part is 0.05, then this part will be, and that part will be, isn't it? So this section, the lower end is this, will be having same probability as that of the right side, the right hand tail, because they are symmetric curve. So these regions which I have denoted by the probability, this is of this I have denoted by the probability 0.05. This region is actually called the rejection region. Rejection region, or it is also called, sometimes it is also called critical region. And the probability which I have denoted by 0.95, this region is called acceptance region. So this critical region and in this acceptance region, they are complementary to one another. Okay, so remember the definition of level of significance. It is the probability of committing the type 1 error. Now let us go back to the table which I drew over here. we already know that probability of committing type 2 error, according to our notation, probability of committing this error is beta. What is beta? Beta is called the probability of X failing to reject the null hypothesis. I'm writing here failing to reject. Failing to reject the null hypothesis when H naught is false. So obviously, if this probability of this cell is beta, and you know the total probability is always 1. So probability of this section is 1 minus beta. So what you are doing over here, you are rejecting the null hypothesis when null hypothesis is false. And this sort of probability, if you can do, it is known as power of the hypothesis testing. It is called power of the test, or power of a statistical test. So in the next page, I'm going to give you the formal definition of this particular term, power of a statistical test. So I'm going back to the next page and I'm going to write the definition of power. Okay. Power of a statistical test, it is the probability of rejecting H naught when indeed the H naught is false. If H naught is false, then alternative hypothesis H1 is definitely going to be true. Now, if you can do so, if you can reject your null hypothesis when it is indeed false, that means your sensitivity of your statistical testing is too high. If you are going to test something, you have selected a sample of some size, and suppose by your experience you have designed your null hypothesis and you are testing it. Now, what you are doing is that on the basis of the sample, you are going to accept or going to reject your null hypothesis. You have rejected your null hypothesis. Then you have studied the population. You have tried to get information from various sources. And you have known that you have rejected a null hypothesis which was actually true. Then you have committed a type 1 error. And after that, you are still thinking that whether this error is the error which has been done by you, or whether this error is because of some inherent nature of the sample that you have chosen. The person who has given you the sample, can he be believed? So you have decided to test your same strategy or same hypothesis 5 times, again 5 times. You are going to repeat your test 5 times more, by each time selecting samples from various heterogeneous uh, areas, or by choosing your sampling method appropriately. In these 5 repetitive experiments, you have come across that the first experiment that you did was actually a biased one. It did not reflect the actual scenario, but in the subsequent 5 testing, you have come to know that the situation of null hypothesis is actually that the null hypothesis you have assumed is actually false. Your experience is showing, and each time your sampling is also reflecting that. Then you can say that the first testing that you made on the basis of the sample, that testing was error prone, but your subsequent testings were actually of high sensitive nature, because you are actually rejecting a null hypothesis when it is actually false. So always remember, if I go back to the table, this part is very highly sensitive part. It is, if anybody can reach to this particular part, or anybody can justify this particular part properly, then actually his testing has reached its high sensitivity. Okay, so this is all about hypothesis testing errors and their probabilities. Now you already know that we have done the hypothesis testing problem by following certain ways. What are these ways? We designed I'm writing the steps once again. The steps to do the hypothesis testing was like that. Set up your H0. Step 2 is set up your H0 and H1. Step 2 is what? Choose a statistical tool and step 3, calculate with given data. Step number 4 is draw conclusion. And I have already told you that in drawing conclusion, you actually do various things, like if you are using the jet test, then you calculate mod z. Then you test whether your mod z is greater than 3 or your mod z is less than 3. If your mod z is greater than 3, you reject. If your mod z is less than 3, then you again test it for different levels of significance, predefined level of significance, either 5% or 1% mostly. So this is the usual process. But in this usual process, there is a kind of thing which may creep in. There is some sort of there is some sort of problem that may appear in dealing with hypothesis testing. What is that problem? One way to report the results of a hypothesis test is to state that the null hypothesis was or was not rejected at a specified level of significance. You know that very well. So whenever we are declaring something about the population, be it population mean or population standard deviation or whatever, and if I say that the population is rejected at this level of significance. This statement of conclusions is often inadequate because it gives the decision maker no idea about whether the computed value of the test statistic was just barely in the rejection region or whether it was very far into this region. Furthermore, stating the results this way imposes the predefined level of significance on other users of the information. This approach may be unsatisfactory because some decision makers might be uncomfortable with the risks implied by the predefined level of significance that you have assumed. So, to avoid these difficulties, the p-value approach and a different kind of approach is actually considered. That approach is called p-value approach, p-value. And p-value approach is actually adopted widely and it is in practice globally. The p-value is the probability that the test statistic will take on a value that is at least as extreme as the observed value of the statistic when the null hypothesis H0 is true. I have done my calculations on the basis of drawing assumption on the basis of drawing assumption from the population and doing the calculations on the basis of the sample. And I actually gave you certain rules by which you either can accept or you can reject the null hypothesis. But right now, because of the problem that I have stated, and actually I'm not writing anything because right now, because I know the time is short, because it's already 5 minutes. And if I start writing, explaining the things, I will not be able to complete it in time. So that's why I'm just explaining it. In the next session, I'm going to make you understand properly that what I'm talking about, what is p-value. So what I'm going to do is that the way by which we solved problems in the previous cases in our previous classes, I'm going to take a problem and I'm going to explain the problem with respect to the p-value approach. Now, as the time of this class is running out, I'm asking all of you to copy the problem which I'm going to share right now with you. This problem you just copy in your note down in your copy, and I'm going to explain the situation with you according to the p-value approach. Now, if I write the problem, it is too long. As you can see, if I write the problem, it will just take time. So please, you do it by yourself, and I'm reading it out for your so that you can easily copy it. Okay, so the problem is very simple. You can easily do it with the help of the earlier approaches that I have shown you. The question is, aircrew escape systems are powered by a solid propellant. The burning rate of this propellant is an important product characteristic. Specifications require that the mean burning rate must be 50 centimeters per second. We know that the standard deviation of burning rate is sigma equal to 2 centimeters per second. The experimenter decides to specify a type 1 error probability or significance level alpha equal to 0.05 and selects a random sample of 9 equals to 25 and obtains a sample average burning rate, which is this centimeters per second. What conclusions should be drawn? This is the problem that you are going to note down in your copy. I'm going to explain this particular problem in the next class. This sort of problem has already been explained many a times. You can very well understand that this is actually falling into the category of test of significance of single mean. Okay, so I'm going to use the formula. You know that I'm going to use this particular formula, x bar minus mu by sigma by root over n. And you can very well get the value of Z. So you note down the problem, try to calculate the Z. I have provided you the formula, and then I'm going to explain the scenario in terms of p value in the next session. So I'm going to stop my recording at this stage, and we are going to explain the thing in the next session. I'm going to discuss the given problem which is there in front of you on the screen with the p-value approach.